So we need to know our volume of the flow. What else?
Pressure.
Sorry?
The pressure.
Pressure, can we be a bit more specific?
Like pressure goes.
Yeah, so the pressure that the fan can overcome to deliver the CFM, right? So, yeah, I'm gonna put pressure here. What else?
RPM.
Sorry?
RPM.
RPM, yeah, ripples. Okay. Anything else?
Speed.
Speed would be the RPM. We could do brake horsepower. Okay. And fan, we can also do type. Because remember, our fans came in different types, right? We had inline, centrifugal fan, axial flow fan, these sorts of things. Good. Heating and cooling equipment. Any thoughts?
BTU output.
Yeah, okay. So let's say capacity.
Heat loss.
So I'm going to put capacity, and off of capacity, I'm going to put heat loss, heat gain. Okay? What else? What could that equipment look like?
Type.
Hmm?
Would it be type?
Sure. So let's say, yeah, let's just say type.
Do outdoor conditions fall under heat loss, heat gain?
Yes. Let's qualify the type further. What ways can we add or remove heat?
High body horizontal.
Sorry?
High body horizontal. That's
Horizontal.
the
Like
layout.
types of furnace.
The type.
Oh, you're typing
Straight
furnace.
or it's a furnace.
Oh, I see what you're saying. Okay. So let's focus just on the part that produces heat there, less on the overall package. Because the overall package, if we talk about a furnace, now it's got our fan built into it, right? So you're certainly right, that was something we used, but I want to get far more specific about this.
Type 1, type 2, type 3, and type 4.
In regards to,
Efficiency.
Yeah, efficiency and also the type of ventilation it's attached to it.
okay, like a house type, type 1, type 2, type 3, 4 house, I believe.
Yeah, type 1 is basically has
This like efficiency ratings?
Yeah, like
for-
the categories of
for
appliance, like residential appliances, where you have like.
Gotcha, okay, so if that's the case, when we're talking about furnaces, I think what you're really talking about, we're talking about combustion at that point, right? So we're burning something to create.
So are you thinking like hydronic
Yeah, that's kind of what
and
I'm,
then gas?
combustion
Versus air.
versus, let's say, hydronic, which would go back to combustion potentially at some point, right? What else?
Geothermal.
Okay, geothermal will branch under hydronic because we're moving water through it. What else?
Like refrigerant kind of.
Yeah, the refrigerant, so I'll put DX, okay?
What does DX mean?
DX stands for direct expansion.
Okay.
So if you think in your refrigeration circuit, when we go past the metering device and that refrigerant flashes and expands, that's what we're talking about. We could also have absorption, like an ammonia chiller, but I'm not gonna bother. Let's call it DX. That's good enough, I think. What about controls?
Humidity.
Sorry?
Humidity.
So you're thinking humidistat.
Yeah.
So let's say temp humidity.
Temperature control, like a T-stat.
So I put here humidity percent, but the other thing is we don't have to do that by relative humidity, we can do it by dew point as well, or wet bulb temperature, but it's just easier writing humidity. What else?
thermostat.
Thermostat would fall under temperature humidity.
Okay. High limit.
Okay, so safeties, sure. I'll put safeties. What else?
You got damper controls?
Dampers, okay, so we do have dampers here, but I'm gonna put it again, because we certainly do that. Now, what do dampers do?
Redirect airflow.
Yes, they can redirect airflow. There's something else they can do.
Open and close the duct.
Cut off airflow.
They'll control our volume, okay? They control our volume by imposing a pressure drop, okay? Do you recall last week when I talked about the fan curve? And we're gonna look at that, right? So my CFM is here, and my delta P, my pressure drop is here, right? So as my pressure drop increases, or the higher my pressure drop, the lower CFM my fan moves, right? So if we want to control the CFM that flows through a duct, we can close that damper, which will create a restriction, induces a pressure drop, and now less air moves through it, okay? So dampers can be directional. We also have volume control, and we also have binary. It's open or closed, it's on or off, okay? What do we need to know about our grills and diffusers and registers?
Can controls also manage like mixing? So like out there?
Controls definitely can manage mixing. That would incorporate dampers. You have, so for instance, are you familiar with an economizer on a rooftop unit?
Mhm.
So an economizer will typically have the economizer damper and a return air damper, and it will regulate that to get more from the economizer outdoor air versus and less from the return, or more. And that actually gets really interesting when you're trying to coordinate. Just as an aside, I designed a makeup air unit once from scratch, and when it came to the dampers, we actually had to look at what's called damper authority. This is a little bit more than you need to know here, but controls, and we might see this in hydronics, are not necessarily linear, okay? You'll have a linear control that, using the same chart here, this would be an example of a linear damper, right? It follows a very nice path where every change in pressure results in a corresponding change in flow. But a non-linear damper might look something like this, okay? Where we don't have the proportional change in CFM compared to the change in pressure. And what that means is if you're trying to do a mixing situation like an economizer, you have to select your dampers so they have the same amount of authority, or a complementary authority, right? Because you want those to work together. If one's linear and one's not, then that damper position is going to let different amount of air through and they might not match. Okay? Grills, diffusers, registers. What do we want to know about them?
Size.
Sorry?
Size.
Size, but the size is relative to some other things. So,
Volume.
sorry?
Yeah, never mind.
Okay.
Where they are on the roof?
Where they are? Okay. Location?
Tight.
Location. Type. Now, when you said size, I'll give you something a bit specific. Let's talk about the free area, okay? So if you have a look at that return air grill in the back is not a great example. Well, it's kind of far, but if you have a look at that return air grill, it's like a 1/2 inch metal spacing, right? 1/2 inch grid. So the whole area of that is not free for air to pass through because we have metal in there, right? So the free area, or the K factor, is what the air sees, and that relates to the size. Different types will have different K factors or different free area. So I'm going to put free area / K, okay? What else?
Pressure drop.
Yep, delta P, very important. What else? Do you guys hear anything from those diffusers right now?
Sound.
It's a good thing. Sound, right? So we're gonna call that NC, noise criteria. we can select our diffusers based on either velocity for sound, where we'll say, okay, we can't exceed 1,200 feet per minute through that diffuser, or we'll look at the published NC ratings on the diffuser and get that. Okay? We're also concerned with, actually, off of location, I'm going to put throw and drop. Okay? Because that'll inform where we put it on the location. Our throw is the horizontal distance at which that air is thrown and at what velocity. Okay? And our drop is that kind of vertical drop. Okay? There was something else I wanted to, noise criteria. ADPI, which I can't remember off the top of my head exactly what it means, so I'll have to look this up, or what ADPI stands for. Just Air Diffusion Performance Index, that's what that stands for. ADPI, Air Diffuser Performance Index. Okay. And that relates to the function or the dispersal pattern of that diffuser, and that's actually based on cold air. We don't have published ADPI for hot air. This is all stuff that we're gonna cover throughout this course, so we're just trying to kind of get a sense for all the things that we need to cover or consider when we're designing a system here. Well, that should be ADPI, not APPI. Okay. Duct. What else are we concerned with our duct?
Like the run length,
Sorry?
length of it and pressure drop.
Yep. So I'm going to put length, delta P, which corresponds, actually, there's a better way to do that. My delta P involves my length and roughness, right? Okay. What else?
The size of the duct?
Size of the duct. So that'll correspond to my delta P. So we can put that there. Let's say free area.
What about the thickness of the metal?
So the thickness is immaterial. Actually, no, that's very good. Sorry. It's immaterial to the pressure performance of the system. The thicker the duct is not going to impact the pressure. What it will impact is the sound and the ability to install it properly. So the bigger the duct, the thicker it must be. So perfectly docked.
Shape.
Shape. Excellent. Okay. What else?
Material.
Material. Why is material important?
In case you're like ducting out of mine and you need like plastic instead of.
Yeah. For dealing with corrosive.
Yeah.
Where might you guys deal with corrosive fumes?
Flue gas.
Flue gas, but piping, right? Not necessarily ducting. That's not fair. It's still ducting, but it's not the duct we're really speaking about. What else could you encounter corrosive gases that get the duct?
Swimming pools.
Swimming pools is a very common one. Okay? Outside of industrial settings, that's going to be your most common one. What else?
Connections.
Connections, fittings. So I'll keep that under delta P. One thing that relates to delta P, but I'm going to give it its own branch, is PSI, or pressure, internal pressure in the duct. Okay? The higher the delta P, the more pressure we need to start with. The higher pressure, the more that's gonna wanna leak out. So we have to improve our sealing, okay? And it might even be like, I told you guys, and we'll see this more as we discuss it, but how duct is connected to each other, okay? When you buy ducts, rectangular duct, you get it in two L shapes, okay? Like that. So they pack together quite well. And they have what's called a Pittsburgh lock. So if you looked at the duct, that's my duct. And shit drawing freehand isometric. Okay, that's my duct. So this is the Pittsburgh seam right here. And what that looks like is you have a tab that's bent like that. Okay, that's one side of the L up here. And then you have a tab that's bent over like that, and you hammer that over flat, okay? That's fairly tight at low pressures, but at higher pressures it'll start to leak. You need to seal that, okay? The other thing is how the ducts typically connect together is called S and drive. So you have, if I'm looking at this on the face like that, you're gonna have drive here on the sides and S here on the top and bottom. So the S is a S-shaped piece of metal. One tab of your duct or one end goes there, the other goes there. Also very leaky. On the drive side here, you bend back at flange and you use, so basically if you had two pieces of duct, I'm looking at the top now, two pieces of duct connecting like this, you would have one flange bent back this way, another here, same here. And you would have a C-channel piece of metal called drive that slides over that, pulls the duct together, and you bend on the top and bottom. Also very leaky and not very strong. When you get to higher pressure ducts or heavier ducts, now you have to have things like standing S, which is not just that S-shaped piece of metal, but also an angle incorporated into it. You might have flanged connections that have to be gasketed and bolted together. There's a lot of different types here, connection types to consider. Okay? Filters. What can we talk about filters?
Thickness?
Like size or, yeah, you said thickness or material even.
Okay, so the material is
Because if you have like an EAC, you'll need a metal
EAC or EML, I'm not familiar with.
electric air cleaner.
Oh, okay, right. So electric air cleaner is not actually a filter. It uses electrostatic charge to
But it does have
pull.
those metal grills in it.
It does, but we distinguish that differently from a filter. It's because it's a completely different mechanism. So a filter will have a physical membrane that will capture particles either through direct impaction or these sorts of things, which we'll get into. So an electronic air cleaner,
It just zaps the particles. Like it.
yeah, it charges them and has an opposite charge plate that draws to them, but wouldn't be considered specifically a filter. MERV rating. You guys heard me talk about that. Minimum efficiency. It's too early in the morning for me to remember what that is. But that's the efficiency or effectiveness of capturing particle size. Okay? The higher the MERV rating, the finer the particles we capture, but also the higher the pressure drop. To counter the pressure drop, we can increase the free area. We can slow the air down because we've given it more free area. And that's what pleats in filters do, okay? So we'll have, again, free area, and we're concerned as well with leakage. If we're bypassing the filter, it's not actually doing anything. I'm pretty satisfied we've gone through everything we have to consider.
Is there anything we have to do with dampers?
With dampers up here, we could do type.
Like fire?
Yeah, actually that's a good point. So fire dampers, we'll just have that under, so we'll have control, fire, Yeah. I think that's, oh, leakage. We'll also put leakage. Okay. Oh, insulated. I'll put insulated with a question mark. It's something I need to consider. If I'm putting a damper in an exterior wall, I want it to be insulated because I don't want a hole of no insulation. That's not very efficient. I also want a low leakage because I don't want that air leaking into the building. We didn't talk about insulation. I'll put that down here. Insulation. What kind of insulation might we have? Actually, that really should come off of duct, but whatever. We'll talk about it.
Sound insulation?
Sound, you said?
Yeah.
Acoustic, good. That's typically a lining that goes inside the duct. How could that impact my duct system?
Make it quieter.
Sorry?
Make it quieter.
It'll certainly make it quieter, but what else?
Also more
Like air
pressure drop.
Pressure drop, right? The fibrous lining inside a duct is not as smooth as the duct wall itself, so we're going to have an increased pressure drop. So we can do that. Delta P. Acoustic insulation, this is something I want everybody to remember now, okay? And for the rest of your career. Acoustic insulation is not thermal insulation. I'm going to put thermal here. Properties of thermal insulation. One, we have R value. Does acoustic insulation have an R value?
It should.
Everything has an R value. Everything resists, everything conducts. It's just how much. Yes, it has an R value. No, it is not sufficient to meet our thermal insulation requirements. The other thing, thermal insulation has is a vapor barrier. And that is, in my opinion, even more critical than acoustic insulation, or than R value when we're comparing insulation, thermal insulation versus acoustic insulation. The reason I bring this up is because in my career on the design and construction side, I've heard time and time again, we do not need to insulate that duct. We've acoustically lined everything. One, if you've acoustically lined everything, my pressure drop is way higher than design. That's not good. The other thing is, acoustic insulation is not a replacement for thermal insulation because the R value is not high enough. Even if it was, I need a vapor barrier. So think about if I have cold air going through my duct in a warm, humid space. I have the insulation on the outside, I have my R value, but I also need my vapor barrier, otherwise I'm going to get condensation on the outside. If we put the acoustic insulation instead and treat that as our thermal insulation, we're still going to get condensation on the outside of the duct. Okay, that'll damage architecture, that'll cause corrosion.
The acoustic insulation is the insulation that's inside the duct.
Yeah, it's a fibrous insulation, kind of like fiberglass, but I think it's made out of something different. And you buy it in like 1/2 inch or 1 inch sheets. When they take their L-shaped duct like this, they apply what do? They first weld these little metal pins on it.
They spot weld them, right?
Exactly, they use a spot welder to put pins in it. They put an adhesive, a glue, that is very noxious, and they put that insulation on to the glue, and then they put these retaining clips onto those tabs that they put on. There's downsides to acoustic insulation. One, like we said, there's an additional pressure drop. Two, it holds onto dirt and stuff really well, so that'll increase the pressure drop over time and cause dust bunnies and stuff in your duct.
Can you not install it externally?
Well, no, so you can't, because part of the reason we put acoustic insulation is, think about the sound vibrations, right? When I'm talking to you now, what you're hearing is my vocal cords vibrate the air coming to your eardrum and vibrating your eardrum, but it's also bouncing off of the hard surfaces. That's what happens in our duct. We generate noise and it bounces off those duct walls. So the acoustic lining goes on the inside, so it starts to absorb that noise rather than bouncing it.
Doesn't it also like make the duct size smaller on the inside? Reduces the. I don't know.
Very good. That goes back to my delta P. That affects my delta P, my pressure drop, in two ways. The first is we've changed the roughness of the duct. There's a lot more friction now. The other way is we've changed the free area of the duct. If I have 1 inch insulation, acoustic insulation, now I've really decreased my duct size by 2 inch on each dimension, haven't I? So I have less free area. So what you'll often see on plans is that the contractor is to increase the duct size accordingly. What that tends to mean is if you put 1 inch insulation on each one, I want you to increase the duct dimensions by 2 inches on each side. That will address your free area. It doesn't address your roughness, okay? Which is part of the reason we don't acoustically line everything. Unless it's critical that we do. There might be some applications where you definitely want it. Let's say,
Supply.
sorry?
A supply.
Like a supply duct.
Supplier or returner.
Both.
So would it just be a situation where like you just acoustically line like a quiet room right above it, and then the rest like through the hallways would not be lined?
Yeah, so typically what we do is we acoustically line the first 10 feet from the fan, supply and return, or the first 10 feet from, let's say, you know what a VAV box is? So a VAV box is a type of damper. It's a variable air volume. It opens and closes to adjust the amount of airflow to the space. That'll cause a lot of turbulence off the discharge, so we want acoustic lining and flex duct to absorb some of that. Where we might do acoustic lining the whole way is if there are sound critical environments like perhaps, let's say, museums or recording studios, libraries. Even still, I don't think we're going to acoustically line the whole library, but there might be parts where we want to do that. We have to take that into account and design around it, because now I have a very different friction factor than what my duct says. Okay, that's more of an extreme case. For all intents and purposes, we're only going to acoustically line the first 10. Okay? I'm sure I'm forgetting something, but this is a lot of stuff, right? And this is stuff that I do have to consider with every project I do. Okay? We don't necessarily evaluate it in this way, and this far in my career, a lot of this stuff is pretty intuitive and just done in the back of my mind with experience. But for you guys, this is something you very consciously have to think about, okay? When I approach a duct system, what do I need to factor in? What is my goal? What am I trying to achieve here, okay? Does anybody want to take a photo of this before I erase it?
Yeah. Yeah.
Actually, you know what? I might have room to do what I want to do here. So I'll leave it up for now until it becomes an issue. So we're going to do a very light example of the process, hello, for designing a very small duct system. Okay? I want to do this in black. Okay, not to scale, but what have I got here?
Washrooms.
Okay,
Washrooms.
we We got washrooms. Okay? What are we gonna try to, or why are we gonna design a duct system for a bathroom?
Why?
Why?
Smells.
Smells? What else?
Moisture control.
Moisture, right? Humidity. There's water in a bathroom. The toilet flushes. Has anybody seen examples of the toilet plume that happens when you flush?
Yeah.
Yeah? It's gross, right? Anybody know what I'm talking about?
When
Yeah, okay.
the toilet
A lot of droplets of moisture. Yeah.
so much water.
Yeah, it's a moisture plume. You flush that toilet, and this plume of water droplets comes straight up and all over your toothbrush and stuff, and it carries with it poop particles and everything else. Okay, pretty gross. Close the lid when you flush in a public bathroom. That's my advice. Okay, so we do want to ventilate this. We want to exhaust this. Okay. Now, if you were going to start with this, and based on what we discussed here, what information do we need to design an exhaust system for this?
Like minimum regulations.
Okay, so yeah, so like what are the codes that inform this? Okay? How might they influence this? What information do you think we might get from this? And I know you guys don't know it. I'm just trying to pick your brain and see if we can go through logic.
Repeat the question?
Yeah, so Andrea suggested that we start with the regulations. What regulations might apply here? What information are you hoping to get from those regulations, Andrea?
There are probably requirements based on like the size of the room and
Okay.
how much airflow you require.
Okay. Airflow is what I was hoping to get at. Size of the room, yes. Building code covers that. We don't care about that. That's the architect's problem. In fact, most of this is already done this is all done for us by the architect. Now, as a plumbing designer, I had to learn how to select how many fixtures we need based on the occupancy and the amount of people and the occupancy type. However, the truth is I never do that. Architect figures that out. They show me where they want what fixtures. I then design the fixtures and the plumbing to serve it. Okay? So that part is governed by the architect for the rooms and all that. We don't care about that. But we very much do care about airflow. You're right. We are going to look at a standard, and this is something you'll want to write down, called ASHRAE 62.1. Okay? ASHRAE 62.1 is ventilation for acceptable indoor air quality. Keyword acceptable. Not good, not great, acceptable. The bare minimum we're required to do by law. Okay? So consider that to be a floor. I have to do this much. There's very good reason to do better than that. That's what takes us from acceptable to good. Okay? But we'll start with ASHRAE 62.1, ventilation for acceptable indoor air quality. As we go through this course, we're actually going to look at ASHRAE 62.1 and figure this out ourselves. I have my handy pocket guide here, which I use all the time for referencing information. Within it is ASHRAE 62.1. So I'm going to look this up and tell you guys what we need to know for this, okay? I know it off the top of my head, but I'm still going to look it up in the table. You know what I don't remember so well? Where that table actually is. Fortunately, there's a table of contents. Air contaminants, and I think it starts on page 50.
What is this book? The ASHRAE Pocket
This thing here
Guide?
is the ASHRAE Pocket Guide.
Oh.
Yeah, very, very handy. Even handier when you can find the information you're looking for.
If you can find it.
So yeah, there is a table of contents, but I lack the patience because like I know where it is, but clearly I don't. Commissioning, it was here somewhere. Oh, Ventilation, there we go. Non-residential, 257 to 259. That's where originally I was looking. Here we go. Okay. So the things we want to know out of ASHRAE 62.1, there's a whole bunch there that we're going to get into later, but the immediate concern is how many CFM of exhaust do I need, or how many CFM of outdoor air do I need, and what is the class of air, okay? The class of air refers to what kind of contaminants are in it, and what can we do with it. How close can we discharge that to an intake? Can we filter it and send it back to the place, into the space, okay? So under ASHRAE 62.1, I'm concerned here with exhaust rates. And this is a toilet public, and I have two rates, 50 CFM per fixture, and when we say fixture, we're not including the lavs, the sinks, we're only concerned with either the urinals or the water closet. So 50 CFM / 70 CFM, and we'll talk about that in a second, and this is class 2 air.
What do you mean by class of air?
So the class of air refers to the contaminants that are in it, and what that means is, can we put this where we discharge next to, how far does it have to be from an intake, and can we filter it and send it back to the space. So for instance, with class 2 air, we have a minimum of 10 feet between the discharge of class 2 air and the intake of outdoor air, okay? So I need to bring in a certain amount of fresh air, right, for ventilation. So let's say, we're not gonna do this in this example, but let's say I chose to do this with an HRV. The HRV is discharging class 2 air, but the ventilation air I need coming in is going to be class, let's say 1 air. So I have to have 10 feet of clearance between that because I can't risk that contaminated air being drawn back into the space, okay? So 50 CFM / 70 CFM and class 2 air. The distinction between the 50 and the 70 in the notes here is E&H. Rate is for toilet room intended to be occupied by one person at a time. Oh, sorry, that's private. Rate is per water closet, urinal, or both. Provide the higher rate where periods of heavy use are expected to occur. The lower rate shall be permitted to be used otherwise. So now we have to have some context on the expected use of the bathroom. Is it going to be used sporadically throughout the day, or can we expect there to be heavy, intense use at some point? Okay? So what could cause us to have heavy, intense use of the bathroom versus sporadic use throughout the day?
An event?
Sorry?
A place that there's a lot of events?
Yeah, like, can you give me an example?
Like Eaton Center?
Okay, the Eaton Center, so we're talking like a major mall with a lot of people coming through. That toilet's probably gonna see a lot of use throughout the day. Okay, good, what else?
Or even like a break during the day when like a lot of people.
Yeah, let's say the Skydome, well, I guess it's what, the Rogers Center? Skydome forever. If you think when we have an intermission, or let's say during a hockey game, right, in between the periods, that's where everybody goes to the bathroom. You're not seeing constant use throughout the day, but you're seeing really heavy periods of use at this time. In fact, what's interesting is if you correlate the data to water usage in the city, you can actually see, just by looking at the spikes, when the the intermission between periods for a major event was, right? So yeah, so those are our reasons. Now let's just say this is an office, and we're just gonna see regular use throughout the day. We're allowed to use the lower rate, okay? So let's go with 50 CFM per fixture, okay? So I'm gonna put this here, 50 CFM per fixture, class 2 air. Okay. How many CFM do I need in the women's?
200.
200? How'd you get that?
Just multiplying the fixtures by 50.
Yeah, we had 4 fixtures. We we weren't concerned with the labs, so we need 200 CFM. Okay. For the men's,
Same.
Never mind.
Same.
same. 4 fixtures. 2 of them are urinals, 2 of them are water closets. Right?
Is there no difference between toilets and urinals?
Yeah, that's what I was gonna ask.
No, not under ASHRAE 62.1. They say toilets, urinals, or both. So my total exhaust for both bathrooms? 400. Okay.
Seems like easy enough.
And we're done. That's the system. Yeah. So that's the volume I need. Now, what do you think the next step is?
Return?
Hmm?
Your returner or your exhaust?
So the exhaust, and you're probably talking about,
Yeah.
right, my inlets. Yeah. I need to kind of think about my grills, diffusers, and registers. In this case, we're looking at grills or exhaust grills. Okay? So I know I want that, but I also have to consider my distribution pattern. How many and where am I going to put them? Am I going to put one big exhaust grill here?
Are you going to?
Yeah. Does that make sense?
No.
200 CFM from right here? Why not?
Because well, the toilets are on the other side.
Exactly. What is the purpose of this? I'm trying to exhaust the contaminants, right? I'm trying to do a couple different things. I'm trying to keep this space under constant negative pressure because I don't want those odors or moisture to migrate to the rest of the space. This is not just bathrooms free floating out in the ether. This is part of a larger building. I want to control the odor and moisture where it's generated. I don't want to have it move. If you walked right into the bathroom here and then got hit with a god-awful smell, you would not be pleased. So we want to have it closer to the point of contamination. The other thing is, as an engineering professional, what is my first priority over everything else?
That it works.
Nope.
Safety.
Sorry?
Safety.
Health and safety of the occupants. Kind of goes hand in hand, like it's gotta work. But the first thing is, like doctors, do no harm. We've gotta worry about the health and safety of the occupants. So remember I was telling you about the toilet plume? It turns out there's nasty stuff that travels in poo particles. Who knew? There are viruses that can transmit through fecal matter. One of them, COVID. That's actually one thing. Flu and COVID can transport through fecal matter. Okay? And this is actually something that's been well documented in, I believe the studies were actually out of apartments in China, but they had transmission through the plumes from the toilets. Okay? So I'll be honest, this is where I think I'm a little bit more of an outlier in my field, where I'm factoring in that sort of thing. Most probably aren't. But that doesn't change anything. It's not like I'm going to now put the register over the toilet because of that plume. I was going to do that anyway because of the odor. But I'm also recognizing the benefits of putting it right up there because it can capture that plume and potentially help spread or reduce the spread of a virus.
Can you not just like install toilets that only flush with the lid closed?
That's a good option. That's actually one thing I've advocated for. Or just do it with lids, period, right? Because how many public bathrooms don't have toilet lids to begin with? Oh, exactly, right? So give them the option to close it. The other thing you can do, and I've considered this, but I haven't done it yet, is have a very high velocity intake. It's going to be noisy and whistle, but any particulate matter that comes up will now be captured by it.
Like airflow velocity?
Yeah, so even horizontally, right, if this is my toilet. So if you had a bar diffuser right behind this, that was really high velocity. Now granted, I might hang out on the toilet longer than most people, at least that's what my fiance thinks. So it might be very uncomfortable to just have this air rush past my head and whistle. Hey, it might encourage me to get off the John quicker. But that might not be comfortable. So there are things we do to kind of balance these considerations. It might be healthier, it might be more effective, but people might not like it. So it's stuff that I've noodled around with, but it's not something that's I've seen much done. But suffice it to say, we're not going to do this, okay? So what do you suggest otherwise? Where should I put my grills, my exhaust grill?
Maybe center or above the toilets.
Okay,
Oh, the first one.
well, when you say first, okay, so like here,
The first stall.
you want to put one right here.
Yeah.
Just one,
You can put two.
okay? Who else? What's the benefit of putting more?
It's more effective.
Why is it more effective?
The more air gets pulled out.
We're more local to our contaminant source, right? If I put one, let's say, right in the middle, it's going to capture these pretty effectively. This not so much. Okay,
Could you do like a long bar?
you could.
Like
That-
same free area as like a more square shape, but just a long bar across the tops of all of them.
That's an option. And this is something that comes with experience. I don't expect you to know this now, but we'll talk about it. And that's the economics of this stuff, okay? Everything has cost. My job is spending other people's money, but to spend it reasonably. Can I justify the cost and complexity of a design? I can justify putting, like, let's say that egg crate, we call it, that return air grill. I can justify putting a lot more of those in than I can put in a linear bar grill. Linear bar grills are really expensive. They look nice. They're justified in a different setting. So in this room, it'd even be hard to justify a linear bar grill for this. But custom homes or high-end offices, certainly, not bathrooms. That cost at that point is not justified. I personally would do at least two. One over the center here, one over here. Same on the other side. Because every time I add one, there's cost and complexity here. But how much, that's what comes down to experience, okay? What my design looks like now versus what your design might look like is drastically different. But what I designed right in the beginning will probably look a lot like what you guys would do, okay? Over time, I know, because again, I used to estimate, I used to install this stuff, I know how much egg crate costs. And it's the things that aren't, that aren't just what you see. So that egg crate, I can't just put it in the ceiling above the bathroom and call it a day. I have to build a metal box to put that egg crate in. I have to connect the duct to that metal box. So there's these ancillary costs that can creep up on you.
How much does it cost?
That egg crate there is probably about $5 for the egg crate.
And how much would the linear bar be?
Linear bar grill, you're probably looking $80 to $100. And that's for like an off-the-shelf one. Once you start getting into custom, because they'll build whatever you want, but now it starts really costing money.
So when would you use that versus the linear bar grill?
So linear bar grills, the last time I used one would have been this high-end custom home in Richmond Hill, where the things I was after was I wanted a really good throw or curtain of air coming down. So we actually had a stairwell that went up 3 stories and was all glass. So I wanted a nice curtain of air coming down and bathing that glass with dry air. Same if you're doing along, the front of a nice office with really big glass, and they're willing to pay for the looks. Okay? Otherwise, these things, I think, these plaque diffusers, it's been so long, but I think these are about $40 to $50 a piece for these diffusers. These square ones that you're seeing right here. So these are all kind of costs that we have to factor in. So I'm incentivized to keep that number low, but I want to make sure I have effective coverage. Okay? So let's say I'm going to put 2. So I'm going to put one right here, one right here, CFM should those each be? Yeah, 100, right? So I'm gonna put my diffuser tag. This is gonna be, actually let me use a different color. Let's use red again. I'm gonna put E1 is my register type. My size, I don't know yet, but my CFM is gonna be 100. Okay? And that's my tag here. And I'm gonna put underneath typical. Okay? There's no need for me to clog my drawings with a tag everywhere if it's all the exact same. I've got 4 identical grills here. I can just do that and I say typical for all of the bathrooms.
Could you also just do a legend instead?
Yeah, so I will have a legend or a schedule, but I still have to identify it on which diffuser registers this. Because again, this is part of a whole building. Presumably there's going to be other grills and diffusers. Okay?
So if each fixture or bare minimum is 50 CFM, what would you do? Would you upsize it a bit? If that's bare minimum, would you do?
Oh,
maybe like
yeah.
25?
So that's a great point. Okay? Being the forward-thinking designer that I am, concerned with people's safety, yeah, I chose the lower end here. Maybe I would choose the higher end. As well, because the economics here aren't going to change much at that point. What would the consequence be of going, instead of 200 CFM or 400 CFM total, if I went with 70, that would be 140, 280, 280 times 2 is 560, if I did that right. So 160 more CFM. What's the consequence of that? I'm probably not jumping up a fan size. They're just gonna go a bit faster. My diffusers might, or my grills might increase in size a little bit, but they're not gonna change in cost materially. The really only negative consequence here is the fan power. Remember, we talked about our fan loss last week, right? So a change in CFM for horsepower is the difference cubed, right? So if I put brake horsepower, where's my eraser? Brake horsepower 2 equals brake horsepower 1 times CFM 2 divided by CFM 1 cubed. By the way, which fan law is this?
Is it 3?
It's the 3rd fan law. Excellent. So BHP2 is a question mark. I'm going to use a BHP1, or my original brake horsepower, of just 1, because I want to see the relative difference. 1 times CFM2, I said 580, divided by 400.
Or was it 560?
I think you're right, thank you, 560. Okay. What's 560 divided by 400? Sorry? 1.4 cubed. What's 1.4 cubed?
2.7, round.
2.7?
Yeah, well, 2.744, but.
Okay, 2.74, let's do that. So, I increased my CFM by 180 CFM, and it increased my brake horsepower by 274%. Okay? My starting brake horsepower was going to be fairly low to begin with, so it's not the end of the world, but there is a very real consequence here for doing that. That's why it's important to understand our fan laws. Okay? So we can know that these changes might result in something that's undesirable. I'm not worried about this bathroom. I'd be worried about an industrial factory where I'm moving thousands of CFM, because now I have to start looking at my power service.
So would that be expensive, the power increase there?
On this, not likely, but potentially. I have had projects where I ran out of power. Typically where we see this is on a retrofit. I did a dog daycare in Barrie with very, very high cooling loads. Because dogs don't sweat, they pant to reject heat, they sweat just on the tip of their nose and their paw pads. So they have a hard time rejecting heat. Also, dogs come in many different shapes and sizes. If you see like pugs with their stupid little squished faces, they're brachycephalic. They have a hard time panting and a hard time breathing to reject heat. So I wanted to make sure that these dogs were going to be safe. So we had like 13 tons of cooling in this place. The original rooftop unit was like 5 tons of cooling. So substantially higher. Turns out they didn't have sufficient power for the things. So we had to do load shedding and diversification. So what we had was controls that would prevent these rooftops from coming up at the same time. Because the issue we had wasn't when they were running at steady state, it was the inrush current of the starting compressors. So these things happen, you can mitigate it with things like that, like controls, or you also might have to upgrade the service, and that might disqualify a project because of the costs. So it happens. But that's why you have to know your fan laws, because you gotta understand the impact of those changes. Okay? Awesome. So, I've got my inlets. Where's that air gonna go?
Well, can class 2 be recirculated?
Class 2 cannot be filtered and recirculated.
Okay, so it would be exhausted.
Be exhausted to the outside. Okay? Where do we want to exhaust to the outside?
Probably far from an intake.
Sorry?
Pretty far from an intake.
At least 10 feet from the intake, but what are our options? I know you don't have a whole floor plan here, so you don't know what the rest of the building is, so just spitball.
Roof?
Sorry?
Roof?
Roof, go it through the roof.
Wall.
What else?
Yeah, side,
Sorry?
the side or the wall.
Side discharge. What are the consequences of that? What is the impact of going
Well,
up through the
if
roof?
you have an intake above where the discharges, then when it comes up, the intake will just take it back in. So
If you did a sidewall.
yeah, if you did a sidewall,
Okay. So sidewall, I can mitigate it. Let's say I've got my 10-foot separation, so I'm not worried about re-entrainment. But let's start with the roof. What are the downsides of discharging through the roof? Sorry?
Cost,
Why is it costly?
because it might be a longer run to the roof than to a wall.
Yes, potentially. But that has to do, I'll say this. 9 times out of 10, you're right. It's gonna be more costly. Nothing to do with the distance. So let's focus on that. You're on the right track.
More, nothing to do with the distance. So would it be like more power needed?
Nope.
No?
Pressure control?
All of the air conditioned air is going to be like at the top half of the
But you mean like stratification?
Yes.
Not in this case. You guys are here for HVAC technology. Have you guys learned how to do roofing yet? No, because you're not learning to be roofers. We have to bring in another trade to do the roofing. Okay? We need somebody who can cut a hole in the roof that can now restore that membrane so it's watertight. Now, roofing comes in many different shapes. You have built-up roofing, where you'll have your insulation, a membrane, and then tar and gravel over top of it. You might have an EPDM type of roof membrane, like that white membrane that gets laid down on the roof. So you need somebody who can put that penetration in and seal it up, okay? So there's a cost there. The other thing is, it's very, very common to have the landlord dictate what roofer you're allowed to use, because they have a warranty on the roof, so you don't get to bring in your own trade. You gotta use their guy that's gonna honor it, okay? So that's part of the problem with that. Also, over time, that's a point of entry for water, for bugs and whatnot. That's another hole in the roof that's gonna leak hot air, okay? So those are the downsides. Typically, they're offset by the savings in running it across, putting in the wall, penetration in the wall. The other thing is potentially structural, okay? We put an opening in the roof pan, that needs to be reinforced. So you have to have sometimes structural steel around it. Another trade. We used to do structural. I remember as a kid in my summers working with my family's business, I was like 15, 30 feet in the air on a scissor lift with, have you guys ever used one of those powder actuated fastener drivers? So it's a little gun with a 22 cartridge, blank, and you had a nail, and then you put that up against the steel, and bam, fire a pin through the steel to attach it. I don't know if it met code. Things we used to do it differently. We wouldn't do it now. You have to bring in somebody who's qualified knowledge to do that.
22 cartridge as if like a gun?
Yeah, 22 caliber.
Yeah, I remember doing.
So
As a 15-year-old,
Yeah,
that's cool.
yeah, they're fun, right?
Which is not.
So yeah, so we have that. What about side discharge? What sucks about side discharge?
Say that one more time.
What sucks about side discharge?
Like exhausting the air through a wall.
Yeah.
Maybe some people don't like the look of it.
Yeah, that's good.
That's a valid one. The architects don't like them. And let's say the architect is not super, like, isn't against it. How am I gonna finish it? Am I gonna finish it with a big bulky weather hood, like I showed you, that hangs off the side of the building? Nobody likes the look of those. Am I gonna finish it with a more expensive louver? Well, louvers have a lot of pressure drop. We need a lot of free area. So it has to be bigger. Do we have structural concerns now? Do I have to put in a lintel to support that load? How do I make that watertight completely? These are all concerns that we factor in, okay? I'm gonna make an executive call. I'm gonna say we're gonna go up through the roof. Part of the benefit from that is we don't see the termination from the ground, so architects like that. We're not super concerned with bringing in outdoor air because the roof's potentially a big area. We'll make sure that we keep 10 feet of clearance to any intakes, and we'll note that on the drawings. But let's go with that. So what I'm gonna do is I'm gonna show my fan right here, okay? I made a call just for the sake of this example. That's a roof-mounted mushroom fan. My fan's up on the roof, okay? One thing you also wanna be aware of, this is actually something I just learned recently, so that's why I'm sharing it. Remember I said about EPDM membranes on the roof, that white membrane? Animal fats and greases will eat away at that membrane, okay? So if you're exhausting commercial kitchen cooking equipment, you don't want that discharging right on the membrane. So you're not gonna spec a down discharge fan, you don't want it up the stack to carry it away, or you can get a special membrane that you put right around it that is resistant to that corrosion, okay? So I have a fan, how many CFM does that fan need to be? Over 400.
At least 400.
Both washrooms, both women's and men's.
Right, but we're keeping it at the 100 CFM, right? We said we could do the 580. So how many CFM does EF1 need to be?
200.
Yeah, 200.
Ones. So each grill was 100 CFM.
So that's 400.
400.
It's gotta be 400 CFM, right? Conservation of mass. Everything must be accounted for. All the air that gets drawn in there must discharge from the fan. Okay? Okay, now I have to think about how I'm gonna run my duct. Okay? There's a lot of considerations here that don't really apply to this bathroom. For a simple bathroom, we can just do this. I'm gonna go with an end cap. Sorry, this is getting a little hard to see. Can you guys see the green lines in the back?
Yep.
Okay. I'll get a better marker for next week. Like that. Okay? Very simple, very straightforward. Now, there might be times you have to change that routing. What could impact my ability to run my duct that way?
Like steel beams.
Structure that gets in the way. What else?
Electrical.
Light fixtures, right? These are light troughers. These go in a ceiling grid, and there's probably about 4 to 6 inches above it into the ceiling area. If I don't have a lot of clearance there, that might be an issue. What else?
Like servicing, like water, gas.
Yeah, any other pipes? If there's a bathroom above us,
Yeah.
and we have drainage pipes, they take priority because they're gravity. What else?
So a lot that goes into it.
Sprinklers.
Sprinklers?
The sprinkler pipe.
What else?
Oh,
bathroom that we're exhausting, is that the only air that's gonna be done?
Also other ductwork.
Presumably, we wanna add heating and cooling to this space. That might be air. We might just put baseboard electric heaters, but we might have other ductwork to contend with, okay? So I can't always do it as simply as I want, but in this case, it's my example, so yes, I can. You then have to break this down into trunks and branches, okay? So, we're gonna call this one, I don't wanna confuse it because I gave it a tag on my drawing of E1. So, I'm just gonna do, okay, let's do this. This marker's dead. This is exhaust grill A, B, C, and D. Okay? This is trunk 1, and this is trunk 2. This is arbitrary. I just came up with these numbers because I needed to identify the branches. The reason for that is I need to measure the length of each one and keep track of that. I want to know what the effective length is. Remember last week when we talked about the Darcy-Weisbach equation? Okay? We had the Darcy equation which talked about our dynamic pressure. That was the pressure drop of air flowing through that duct. On the top of the equation we had L, right? For length. The longer the duct, the more pressure drop we have. So we want to know what the effective length of each branch is. What we're going to be doing is we're going to be sizing this duct according to the equal friction method. Okay? There is 3 types of duct sizing. Equal friction method, where we size everything so it pretty much has the same pressure drop, and that way no route is favored one over the other. They're all pretty much the same length as far as the air is concerned. Static regain, which we're not going to get into. Remember how I told you with total pressure, we can trade off dynamic pressure for static pressure? I'll explain, or I'll give you some literature to read about static regain. It's not used for supply and exhaust and return. You only use it for supply. You'll see that typically done on high velocity systems, so we're not going to get into static regaining. And then there's also constant volume, which we're not going to get into. We're going to focus on equal friction method. Okay? Now I've split this up into 2 trunks. The first that is going to see 400 CFM, and then the second, after C and D drop off, that sees 200 CFM. Why might I split that up into 2 trunks?
You could reduce duct size after.
Right? So, when we lose mass, in this case when I say mass, we've lost air, right? Or when we gain mass, because we're exhausting, we gain energy. There's more air, okay? So, there's going to be a difference in duct size as a result. This will be smaller, 2 will be smaller than 1. This allows me to reduce the size, which saves material, but it will also allow me to keep the velocity up, okay? Remember that we can trade velocity pressure for static pressure, okay? So I'm incentivized to keep that small from a cost standpoint. The smaller the duct, the less material we use, less material cost. The smaller the duct, the easier it is to install, lower labor. And the smaller the duct for the same amount of air, the faster it goes. When we're dealing with contaminants, that's a good thing. There's a trade-off for sound, but if we're trying to keep the contaminants moving through the duct, we want it to go faster. If we slow it down, those contaminants can precipitate out and not be carried to the exterior. Is everybody familiar with what a river delta is? So, who's been to Vancouver? Okay. Work with me, guys. river. Nobody's been there, I'm assuming, but people have seen it or heard of it. Okay? At the end of a river where it flows into a larger body of water, it's called a delta. From the Greek symbol, delta, the triangle. So what happens is if I have a coast, okay, and then I have a river here, that flow of water is constrained. So it's moving pretty quickly, right? It has high velocity. Once it gets out here, all that water can spread out. In doing so, it slows down, okay? Because it's no longer constrained by the river walls. When it slows down, all the sediment that was coming with it precipitates out, it falls, because the water's not moving fast enough to carry it anymore. So what you see in a delta is that shape, okay? Where it creates this delta fan of deposited sediment. Okay, so you can see that from the sky. And in fact, the reason that the Nile River is like the cradle of civilization, or one of them, is because all the nutrients that precipitate out, that builds up to very good farmland with a lot of water, and that's where you start growing a lot of your food. Okay? So the same idea here when we're trying to keep contaminants exhausted, we want that air going fast enough that none of it comes out inside the duct. We want to carry it with us. Okay? So we're incentivized to reduce our duct size a bit. Now, put yourself in the air's shoes. You are air right at 3 here, going up your grill, on your way to the fan. What do you have to go through at this point if you want to leave the building through this fan?
Ductwork?
Before the ductwork.
The grill?
The grill. So let's say my grill, I've got my ceiling, okay? I've got my egg crate grill. I've got a box up top with a duct connected to an elbow, okay? You have to think about all this as the designer. What's this going to look like? You can't just leave it up to other people because we have to account for all the pressure drops. So if you're the air, what's the first thing you have to pass through?
The free area.
The free area of my egg crate. What's the next thing you have to do?
The fitting? Or like
Sorry?
the 90?
Even before that, all this air has to converge to get into that entrance, doesn't it? That hole is smaller than the egg crate. So we have a convergence there. That has a pressure drop. So I have to account for that. I have to account for that pressure drop. What's the next one?
The 90, is it?
Now the 90. That steals energy as we pass through. Now we're right here. What do I have to do? Where do I go next?
Across your run to the main trunk
I gotta take this, right?
branch.
Okay, so what's the pressure drop there? What would cause that? Sorry?
Distance?
Distance, the length of the duct, and that's just the friction of straight duct. That's gonna be low friction, but there is something there. So we have to account for how many feet that is. For these fittings, we're pretty much gonna give them an equivalent length in feet. Okay? What about here? Now what?
Direction?
I gotta turn 90 degrees, right? But, am I all by myself? Is it just 100 CFM with nothing else going on? There's already 100 CFM from here. Now I have a converging airstream. That takes energy. Think about merging on the 401. Well, 401's not a good example because everyone's going so slow anyway. Faster highway, where everybody's doing $1.20. And now people are trying to merge. Cars have to slow to let you in, you have to slow to keep pace, so that takes energy. So we are robbed of energy at the convergence. What next?
So my fault, sir. So it doesn't work as if it would speed up, it actually slows down?
Yeah.
As if, no.
It slows down, because remember how I told you that all those molecules at their energy state have that room that they love to vibrate, and personal space, other molecules can't get in there, right? So they don't want to come close to each other. So there's going to be that restriction.
Because they're forced to.
Exactly. Okay, so we got a pressure drop there. What's the next pressure drop?
The duct again.
Sorry?
The duct again.
Yep, straight duct through here. Next,
The next branch.
convergence, we have to slow to allow it. Same with the other one, right? There's one thing I didn't show here, but we discussed that you might be able to infer it. We have a change in size, don't we, between trunk 1 and trunk 2.
Your transfer.
So I've got a transition fitting. So I'm going to draw a triangle here to show that I get smaller. That's another fitting. Okay? Remember I told you about the delta? That's the same thing in that fitting, right? The duct got bigger, so the air slows down. Okay? So we have a pressure drop there. Another convergence, then straight duct. This could look different ways, up to the designer. On my roof, here's my roof deck, and here's my terrible looking mushroom fan that discharges up. I can just have this as an elbow that goes to my duct, or I can just have a box that goes straight down and then tap my duct in it. That's a cheaper way of doing it, because fittings aren't exactly cheap, okay? But that's a much higher pressure drop. We have to know that, we have to decide that, okay? We have to communicate that to the installers. So there's another pressure drop here. What about a flex connector? I might want a flex connector there because that fan's going to vibrate. I don't want to transfer that vibration to my ducts, because that'll be annoying if you hear a rattling while you're trying to use the bathroom. So I'll have a flex connector. That has an additional pressure drop. Okay? So we would look at all of these and figure out what our equivalent length is. And then we're going to size our duct based on an equal pressure drop, because we want all of these to have the same equal friction. We don't want one favored over the other. Okay? So we would create a table and we would go through and identify all these fittings. So let's say we have branch A, B, C, D. For this part here, I'm just making these numbers up, okay, just to keep the conversation moving, but we would actually look into this and figure this out. So we can look at either a pressure drop in inches water column. So maybe this is 0.04 inches water column, or we could even go as far, depending on the residential way we did it, we could say that has 20 feet of equivalent length. That friction loss is the same as if we had 20 feet of straight duct. Okay? So you identify this and you record it all. So let's say our terminal is 20 feet. They all have the same terminal. So you take 20, 20, 20. You would look at your 90s. How many 90s do I have? For A, I have 1. That is not we wouldn't consider that a 90, we would consider that a takeoff, because there's convergence. So I only have 190, and actually let's say I have another 90 here, okay? So I have 190 when it comes there, 190 when it goes up to EF1. So all of them have two 90s, right? Let's say each 90 is worth 5 feet, so I got 10 feet. Does A have a convergence? Does it converge with any air streams when it comes here? No, it's all alone at this point. But it converges here, here, and here. Let's say each convergence is another 20 feet. And I'll give you the real numbers later, but say conversion. So A is 20, 40, 60. What about B? 60. Same, right? 20, 40, 60. C? It's just the one, right? Everything else is already in there, so it only converges, so it only gets 20. And D? 1, 2. It gets 40.
Is A also supposed to be 20?
A up here? Or sorry,
Yeah, because A is its own thing.
A is not converging with anything right here. It's still only 100 CFM, but it's converging at this point. It's seeing air come in and meet with it. So that's why I'm saying here's 20, here's 20, here's 20. Does that make sense? Can I explain that another way?
No, it's fine. It's probably not too important.
Okay. But the point is, everything's a little bit different, right? And I'm gonna add here, let's say, I should have put more room, but let's say transitions where the duct gets bigger. Let's say that's 15 feet. Does A have a transition? Yes, because the air from A has to go through that fitting. How about B? Yes. D? No. And C, no, right? So we're only giving A 15 feet, B 15 feet, 0 and 0 for the others. And we do this across and so forth, okay? We can add the lengths of the duct. Let's say each one of these is 10 feet. Let me make myself more room. So this is measured length, and this is A, B, C, D. Okay, so let's say each one of these is 10. So A is 10, and let's just say this is 40 feet. I'm making this up. How many feet is that? 10, 40, 50, right? 50 feet. B looks like we're about 5 feet less. 10, 35, 45. C is 10, 20, so 30. And let's say D is the same. Okay. So now we can add up our total length. 50, 70, 80, 140, 155. 45, 65, 75, 135, 150. 30, 50, 60, 80. 30, 50, 60, 100. Pretty different lengths, right? Physically, they're actually not all that different. But what the air sees, that's a different story. Okay? So what we're trying to find here is our longest run. Which one has the longest run? A. That is the most restrictive path. So that is what we would design around us, okay? We would then figure out a pressure drop in straight duct to come up with a size for that, okay? And then we would have it so whatever size we select for the other one, depending on the length, they have the same friction. So what that means is C and D are fairly short runs compared to these two, right? So C and D could actually have a smaller duct diameter than A and B. Why might that be? What happens for the same amount of air if my duct is smaller?
The velocity goes up,
Sorry?
the speed of the air will increase.
Exactly. The velocity goes up. It has to go faster, right? What happens when my velocity increases?
Volume,
Sorry?
volume will increase.
No, the volume. Oh, the volume of the duct or air, you mean?
Air.
No. So for the same amount of volume, for the same amount of air, if we have a smaller duct, velocity goes up.
Noise.
Pressure goes up?
The pressure drop goes up, right? Remember when I had you guys do this? The faster it goes, the more friction we have. So because these ducts are shorter, I can make those smaller compared to this because I want those pressure drops to be the same. Okay? I want a little bit more friction here and a little less friction here. Because I want the air to see them all equally. If I didn't do that, if I made them all the same size, what would happen?
The air will not move from the long one.
We would have less air. Instead of the 100 we were asking for from A and B, we might get 80. And instead of the 100 we were asking from C and D, now we might get 120 out of each. It's not balancing, okay? So we want it to be, that's what we mean by equal friction method. Regardless of the length of the duct, we want them to have the same frictional loss or the same pressure drop. That way it will be self-balancing. We still need balancing dampers, because nothing's perfect, but that's the intent. That's what we're going to do in this class. We're going to do this in much greater detail, okay? Now, we figure this out, and I get a pressure drop, making this number up, but my pressure drop is 0.3 inches of water column. What do I need to do now?
It has to be the same pressure drop for every branch.
That's going to be my total, and that's measured based on the longest run. That's what dictates it. With the idea being, if I have enough pressure to overcome the resistance of this, I have enough pressure to overcome the resistance of the rest of it, because they're going to be less restrictive. But where does that come into play? When I say I need this much pressure, what produces that pressure?
Fan?
Horsepower fan.
Well, yes, the fan, right? So that goes back to my fan performance. Now I'm going to look at my fan curve. So on my fan spec, and again, we'll look into the fan curves later, Q, which is flow, so CFM, and this is delta P for pressure, but I'm also going to put on the same axis in blue BHP, the brake horsepower, okay? Because that's where they typically put it on the fan, or on the curve. So, my system curve looks like this, okay? The more flow I have, the higher the pressure drop, right? As I try to move that air, more air through the duct, the faster it goes, the more friction there is, and the more pressure drop. That's why our curve builds. The higher our CFM, the higher the pressure drop. That's my system. My fan pressure does this. The higher the pressure of the fan, or the pressure drop of the fan, the less CFM it moves. As that pressure drop reduces, there's less friction, we can move more air. Where do those two intersect? That's where I want my fan to run. I want enough RPM to achieve that. I need enough brake horsepower to achieve that. Okay? If my system actually ends up being less resistant than I thought, what would that look like? That would look like this, let's say. Okay? Then we would find our operating point actually shifted down here. Okay? That's a very simplified approach to how we do this and all the things that we need to consider. It goes a little bit further. We didn't even talk about balancing dampers. which we would want to factor in. We're not concerned with filtration on this point because we're discharging to the outside, right? If I were bringing in outdoor air, now I'm concerned with filtration. We didn't talk about voltages or anything like that yet. We didn't even talk about sizing our drills and diffusers. I wanted to introduce you to the process. Give me a confidence check. Of everything we've talked about so far, how are you feeling about it conceptually? Good?
Seems very similar to like gas pipe sizing.
Exactly. Why would that be?
Longest run.
Sorry?
Longest run method.
Sure, but that makes perfect sense. Why would this be the same process?
Moving dynamic fluids through.
It's gas molecules. It's fluid dynamics. The physics don't change. The density of our fluid does. The volatility of our fluid does. Natural gas or propane is much more volatile than just straight air.
Same rules apply.
Sorry?
Same rules apply.
But the physics are the exact same, so the same rules apply. Okay? We're probably not going to deal with equivalent length. This is a bit overly simplistic for the approach we take in commercial, but this is how we did it in residential. Does anybody recall that? Or are we learning this for the very first time? It's okay if you don't remember it that well, but I just want to get it checked on who does. Okay? So a lot of what I want to cover here and the value I bring here is this approach, this thinking, okay? Because the truth is, you don't need me for this. You can learn this out of a textbook, okay? Knowing how to think about the problem, how to approach the problem, the experience that comes with what do you need to do, that's where I bring value here, okay? So as we go through this, obviously I'm going to help you with this, I'm going to lecture you guys on this, but there might be a lot more independent reading on this exact method, okay? Because again, that's not where I feel I add value. Right? We go till noon. Is that right? I keep forgetting 1 second. 4 hours, we go to noon, so call it 11:45. Okay, how taxing was this? Is everybody's brains mush?
Yep.
Let's take a 10-minute break, and then I'm going to give you a presentation. I gave it last year, but I'll give it again here on the design method